All right, standing waves. What has to be happening in order to cause standing waves in the first place? What sort of situation would tend to lead to standing waves? Yeah, typically you've got these endpoints, right? One example would be if the two ends are fixed in place. You've got to have, yeah, some sort of boundary. You've got to have some confined region of space where the wave keeps echoing back and forth. And one common example of that is a string. Let's say we've got a string that's fixed in place on both ends. Like for instance, on any stringed instrument. This mandolin, for instance, we've got these strings that are fixed in place at the tuning peg here, and also fixed in place at the bridge here. So that's a string where waves can bounce back and forth because every time it hits one of the ends, it bounces off the end. And that means it's confined to this small region of space, this finite bounded region of space. You could have a pulse traveling along the string and then bouncing back. And if you've got a continuing wave, you've got a wave traveling in one direction and its reflection traveling in the other direction. So this does count as interference. You've got a wave traveling in one direction interfering with its own echo, its own reflection. And if the wavelengths match up just right, then those interference patterns tend to form nice, neat cycles of some locations that are always constructive and some locations that are always destructive. At the endpoints, for instance, if these endpoints are fixed in place and cannot move, what kind of interference does that have to be? Yeah, that's got to be destructive. So standing waves are going to form patterns where the endpoints, assuming the endpoints are fixed in place and cannot move, the endpoints are going to be locations that are always destructive. And we call those locations nodes. So a node is just a location that is permanently destructive interference because of the way the wave and its reflection are interacting with each other. And those are just going to be stationary. These points, of course, don't oscillate at all. But between those, you could have locations that happen to be always constructive interference as the wave and its reflection pass by each other. And those points of always constructive interference are going to be large oscillations, and those locations are called antinodes. And they're going to appear, in this case, let's say halfway between the nodes. They should be evenly spaced. So this would be an example of an antinode. And we typically draw the standing wave like this. What this is supposed to represent is that the top and bottom curves represent the highest and lowest the string can go. So the string is oscillating high and low and high and low. The top curve represents the highest the whole string goes. The bottom curve represents the lowest the whole string goes. So for instance, this point is oscillating as high as this far up and as low as this far down. This point on the string is oscillating smaller amplitude of oscillation. This point is only oscillating a little bit, and of course the end point is not oscillating at all. So that's what this sort of diagram is supposed to represent. The top and bottom curves represent the highest and lowest each individual piece of string goes. Any questions on that so far? So this is basically the simplest shape a standing wave can form. But even if we keep the same restrictions, if we just have a string with fixed endpoints, we could have a more complicated shape, still assuming that the endpoints are nodes. But those don't have to be the only nodes. We could also have a node somewhere in between. In fact, specifically, it would have to be exactly halfway in between because the nodes are supposed to be evenly spaced. So let's say we have nodes on the endpoints, as we should expect, and another node exactly halfway in between. And then between adjacent nodes, what should we expect to find? Like halfway between this node and this node. What's going to be there? Yeah, we should expect an antinode. And likewise, halfway between these, we'd expect an antinode. So the wave pattern is going to look like this. And sometimes the other curve is drawn as a dotted line, just to distinguish between them. So you might see it drawn with like a solid curve and then a dotted curve. But it still represents the highest and lowest that point can go. So what the string would actually look like, if you watch this in slow motion, it's going to be wobbling sort of like this, with the point exactly in the center not moving at all, and these points oscillating up and down, essentially out of phase with each other, one up and the other down at the same time. And then, of course, the endpoints are nodes because they're fixed in place. And we could up the complication of this even further. We could say, same string, still fixed on the endpoints. The endpoints, of course, then have to still be nodes. But instead of having just one node in between, let's say we have two more nodes in between, still evenly spaced, so it splits the rope into thirds, and then antinodes between those. So this would be another possibility. This is another standing wave pattern that can happen on this same string. And keep in mind, these are all the same string. They're just different ways that same string could be moving and still count as a standing wave. And you can add in as much complication as you want. You can have the same string, endpoints still nodes. And instead of having two nodes in between, let's say we have three nodes evenly spaced in between, cutting the rope into fourths. And so your standing wave pattern would look like that. And you could keep going. In order to keep track of these, we usually label these. The first one we're going to call n equals 1, then n equals 2, n equals 3, n equals 4, and so on. The n equals 1 case is also called the fundamental vibration or fundamental harmonic. And then the other ones would be labeled the second harmonic, third harmonic, and so on. So the harmonics are just the various different shapes of standing waves you can get on the same string. And then fourth harmonic and beyond. These are also sometimes called the first overtone. Like the second harmonic is the first overtone, because it's the first one beyond the fundamental harmonic. The third harmonic would then be called the second overtone. I don't really like this terminology because it doesn't match up with the n value. But if you see overtone being used, that's what it's referring to. The second harmonic, n equals 2, is called the first overtone because it's the first one beyond the fundamental harmonic. Any questions on the terminology so far? So let's see if we can establish a numerical or mathematical pattern here. For the fundamental harmonic, for the n equals 2 case, n equals 3, n equals 4, all these harmonics, I find it very useful to count things not in terms of whole wavelengths, but in terms of half wavelengths. Because a whole wavelength would look like this. And note that that is, which one does this correspond to? Which harmonic does the whole wavelength correspond to? Yeah, the n equals 2 harmonic, that one wavelength is the length of the string. So we can certainly establish that on the n equals 2 case, the wavelength is the length of the string. Let's call that L for now. So L, capital L, is just the length of the string. So L is the length of the string. In the n equals 2 case specifically, the wavelength is the length of the string. Let's call that lambda sub 2, the wavelength for the n equals 2 harmonic. But note that these are not all whole numbers of waves. For instance, this is half of a wavelength. This looks like 1.5 wavelengths. It's much more convenient in these cases, instead of counting wavelengths, instead to count half wavelengths. Because half a wavelength will take you from node to node. And since we're going from a fixed endpoint to a fixed endpoint, that means we have to start and end at a node. If you're starting and ending at a node, then you have a whole number of half cycles, 1, 2, 3 half wavelengths. Or for the n equals 4 case, we've got 1, 2, 3, 4 half wavelengths. The n equals 5 case likewise would have 5 half wavelengths. It's very convenient here to count half wavelengths, partly because half a wavelength takes you from node to the next node, so you've got to have a whole number of them. And also the n value, the harmonic number, just tells you the number of half wavelengths in these cases. Any questions on that so far? So let's try writing these out in terms of half wavelengths. For n equals 1, we've got 1 half wavelength. 1 copy of the half wavelength equals the length of the string. Solve that for lambda n, what do you get? Yeah, just 2L. And you could think of this as this is half the wavelength. If you continued it to the other half just doubles that length. So the wavelength, the length of one cycle, would be twice the length of the string. For lambda 2, we could use the same idea. This is 2 copies of a half wavelength. So we could say 2 half wavelengths equals the length of the string. And then the 2's just cancel out, so we get lambda equals length of the string. For the third harmonic, we've got 3 copies of the half wavelength. We can write that as an equation also. 3 copies of the half wavelength is the full length of the string. Solve that for lambda n, what do you get? Yeah, 2/3 L, or 2L over 3. And we could keep this going. In fact, let's see if we can generalize this. Instead of the fourth one, let's try this in general. For the nth harmonic, what would the corresponding equation be? If we're looking at the nth harmonic, how many half wavelengths do we have? Yeah, it should just be n, right? Because the harmonic number, the n, is the number of half wavelengths in this context, at least for this type of standing wave. So for the nth harmonic, we've got n copies of the half wavelength making up the length of the string. Solve that for lambda n, what do you get? Yeah, 2L over n. So the wavelength of the nth harmonic, lambda sub n, is 2L over n. So if we take a look at these specific examples, we've got 2L over 1, that's just 2L. 2L over 2 is L. 2L over 3, 2L over 4 would be half L. Then 2L over 5, 2L over 6, 2L over 7. 2 times the length of the string divided by any whole number, because n does have to be a whole number, will give you a wavelength that will work here. So you can find the wavelength of any standing wave you want just by taking 2 times the length of the string and dividing by any whole number you want. That will give you a wavelength that will work as a standing wave. The in-between values don't work, by the way. If you tried a value between those, like let's say you tried a value between 2L and L, let's say you made the wavelength 1.5L. That's not going to work. It's not going to form a standing wave because that wavelength wouldn't lead to the endpoints both being nodes. Like if we tried making the wavelength a little bit longer, that's not going to work because the other endpoint then wouldn't be a node. And wavelengths only work on this string if both endpoints are nodes. The endpoints have to be the same type of point. Any questions on that so far? And one other thing we want to figure out here is that if this string is oscillating with this wavelength, you don't really hear the note by just like putting your ear on the string. In order to get to your ear, the sound also has to travel through what other medium? Yeah, it's got to travel through the air. The string is vibrating, which causes the air particles nearby to vibrate, and that vibration propagates as a traveling wave. So the standing wave in the string creates a traveling wave in the air. That traveling wave reaches your ear, causes your eardrum to vibrate, and the parts of your brain that deal with sound detect that vibration and turn it into the thought of a sound, the experience of a sound. But that means that in order to reach your brain, these sound waves have to travel through several different media: the string, the air, your eardrum, Every one of those changes in medium is going to change some stuff, but what doesn't change? What's the one property of a wave that doesn't change when it transitions from medium to medium? Yeah, the frequency. If the string is oscillating, let's say 100 times per second, it's going to cause the air molecules nearby to oscillate 100 times per second also. They're going to be oscillating in sync with each other because the string's vibrations are pushing on the air and causing it to vibrate in the same way. So the frequency we can expect to stay the same. The wavelength is going to change. I mean, like the wavelength of sound in air is not going to be the same as the wavelength of the wave in the string. But we can figure out the frequency of the wave in the string, and then the frequency of the sound in air should be the same frequency. So how do we convert this wavelength into a frequency? How do wavelength and frequency tie together? Yeah, we can use this idea of speed. Speed equals wavelength times frequency. So let's use that. Speed equals wavelength times frequency. So frequency is going to be speed divided by wavelength. So we can just take speed, specifically the speed of the waves in the string itself. If you imagine the string as being very long and you pluck it, then that pulse is going to travel through the string. The speed we're talking about here is the speed of the wave in the string itself, because that's where the sound is being produced. That's where the wave is being produced. So we've got speed of the wave in the string, which is going to depend on properties of the string. We divide that by the wavelength, 2L over n. Of course, dividing by 2L over n is the same as just multiplying by its reciprocal. So we can say speed times n over 2L. I'm going to rearrange those factors a little bit. Let's say V over 2L times n. So that's the frequency of the nth harmonic. And this is really convenient because since n has to be a whole number and V over 2L is just some constant, that means the frequencies that this string can produce are all whole number multiples of some baseline value. And specifically that baseline value, V over 2L, V over 2L is just the frequency when n is what simple value? Yeah, V over 2L is the frequency of the fundamental harmonic, also called the fundamental frequency. So let's list these out as frequencies. We found that in general, the frequency of the nth harmonic is going to be V over 2L times n. And this is specifically assuming that the endpoints are both fixed. If you have a different situation, that might not still apply. But let's list those out. Frequency of the first harmonic, also called the fundamental frequency, would just be V over 2L. Frequency of the second harmonic, we just take that same value and multiply by 2. In other words, it's the fundamental frequency times 2. And then the third harmonic, V over 2L times 3. And since V over 2L is the fundamental frequency, this is just F1 times 3. And likewise, the fourth harmonic is going to have a frequency that's just F1 times 4. Fifth harmonic is going to have a frequency that's F1 times 5, and so on. So all the frequencies that are produced here, all the frequencies that can be produced by standing waves in this string, are all these nice, tidy whole number multiples of the fundamental frequency. And when you plug a string, you're actually not producing just one of these. You're producing lots of these at once. And this is really why musical instruments sound the way they do. Have you seen, or have you heard, I should say, have you heard what it sounds like if you're listening to just one frequency? Have they done anything like that in lab where you're listening to just one frequency, like just frequency equals 400 hertz or something? It sounds awful, right? It's just this flat monotone, sounds horrible. But the reason why musical instruments don't sound like that, if I play a note on this mandolin, it's not producing just that one note. Because when I pluck it, I'm not specifically choosing one of these frequencies. I'm not grabbing the string and vibrating it at a certain number of times per second. I'm just putting this chaotic motion into it. I'm just making it move in a jumble of different ways. What I'm essentially doing is I'm creating lots of frequencies at once, but most of those frequencies immediately die off because they don't form these nice, neat cycles. The only ones that actually stay around, the ones that keep going, are the ones that form standing waves. One of those is V over 2L. That's the lowest frequency that's produced by this string, and that's the frequency that you hear most of. But instead of just hearing a flat monotone of that one note, you're hearing mostly that note and a little bit of sort of, I guess you might say, echoes or resonance of a few of these notes as well. So this sound is blocked by the leather strap. That sound is lots of notes being heard at once. Mostly this one, but also nice, neat whole number multiples of it. And nice, neat whole number multiples of the same note sound good together. In fact, if we take a look at exactly how those are related, what's the transition from here to here? Well, how do you change mathematically from F1 to F2? Yeah, that's multiplied by 2. So not only is it just a nice, neat whole number multiple, it is specifically exactly twice as much. And what does that do? If you increase, in general, if you increase the frequency of a sound, what do you hear about that? What does it sound like if you increase the frequency? Yeah, it's going to be a higher pitch. So F2 is going to be a higher pitch than F1. And we can be even more specific than that. If we are specifically doubling the frequency, anyone know how much of a higher pitch that results in? Have you heard of the idea of an octave? Like going up exactly one octave in tone? If we're going from, like, let's say that this is a G. If I also play this, that's a G, and then the next G up the scale. So it's the same note, but one octave up. That transition from low G to high G, that's exactly doubling the pitch. Maybe not exactly doubling because it's a little bit out of tune, but one octave corresponds to doubling the pitch. So going from F1 to F2, that's one octave of transition. And those now sound good together. In fact, they sound so good together that we tend to think of them as different versions of the same note, low G and high G, for instance. But this is what happens when you double the frequency of any sound. You go up one octave. Do you see any more doublings, any more pairs of these where one of them is exactly twice as much as the other? Yeah, if we go from 2 to 4, if you take F1 times 2 and double it, you get F1 times 4. So this transition from F2 to F4 is also a doubling of frequency. So that's also going up one octave. So we've got this fundamental frequency, let's say that's low G, and then F2 is going to be the next G up, a high G, and then F4 is going to be an even higher G, one more octave up. But we've got this other one in between. What's this transition from 2F1 to 3F1? What's the multiplier there? What do you have to multiply 2 by to get 3? Yeah, 1.5. And that's not a whole number, but it is a nice convenient fraction, 3 halves or 1.5. Multiplying by 1.5, increasing the frequency by 50%, or multiplying by 3 halves, that's another nice, neat transition. If I remember correctly, that is a major fifth. So that's going to sound like going from, let's say, a G to a D. And again, these are notes that sound good together. This is the foundation of the idea of chords, collections of notes that sound good together because they are nice, neat whole number multiples of each other or nice, neat, simple fraction multiples of each other. If you take a note and multiply its frequency by 1.5, you get a major fifth up. Or if you take a look at the next transition from 3 to 4, what's the multiplier there? What would it be as a fraction? 3 times what is 4? Yeah, we can just multiply by 4/3. That's another nice, neat fraction of simple whole numbers. And so this also forms a nice sounding tone together. It is, I think that is a major fourth. Yeah. And that is also, we're looking at the bass note, G, a major fifth up from that, D, and then a major fourth up from the D gets us back to the G again. That's all right. So these are, again, notes that sound good together because they are these nice, neat whole number multiples of each other, or nice, neat, simple fraction multiples of each other. And that's ultimately the foundation of most of music theory, notes sounding good together because of the way their frequencies are related, the physics of why chords work. Any questions on that so far? Then let's take a closer look at the formula itself, the F sub n formula, to figure out the frequencies that are possible. If you want to modify that note, let's say you're creating some note with a stringed instrument, or any instrument really, but let's say a stringed instrument for now, and the frequency is not quite what you want. How can you modify the sound it's producing? Like, what was I doing in order to change the note I was playing, even if I was playing it on the same string? Yeah, I'm changing the effective length. When you fret the string, when you pinch down on the string, like if I play this, but versus put my finger on the string, I'm changing the effective length by pinching it. That means that if I pinch hard enough, only this section vibrates instead of the whole thing. So by fretting the string, I am changing the effective length. I'm making the length shorter. And if you make the denominator smaller, what happens to the result? Yeah, you make the length longer, larger denominator, or sorry, smaller. You make the length smaller and you get a higher frequency. And that's exactly what just happened. I fretted the string and plucked it and I got a higher note. Shorter length means higher frequency as a result. So you can change the frequency produced by the same string just by pinching off parts of it and changing its effective length. And of course, the end values could also be different, but you get a variety of different end values from just plugging it once anyway. Like I was saying, you get mostly this note, a little bit of this note, a little bit of this note, a little bit of this note. And that's really what gives an instrument its distinctive tone. The reason why, for instance, a mandolin sounds different from a violin, which sounds different from a flute or a trumpet, is largely because they're giving different mixtures of these. Like maybe one instrument gives you 50% this, 25% this, 25% this. And maybe another instrument gives you 70% this and none of this, and then 10% of each of these. They're all still going to sound like this note, but they're going to sound like different variations on that note, and they're going to sound subtly different because they have different blends of the other overtones. Any questions on that so far? One other question about this formula. You can change the pitch by changing the length, and you do that by putting your finger on the string. But how else could you change the frequency? What else could you modify in this formula? Yeah, you can modify the speed itself. Even without changing the length of the string, you can modify the frequency you get by changing the speed. But how do you do that? What does the speed of the note or speed of the wave depend on? Right, the medium itself. In this case, the string. You can change the speed and therefore change the frequency even with the default length by modifying the properties of the string itself. And what properties of the string do you think are going to matter there? What properties of the string influence the speed of the wave? Yeah, the tension is the main one. If you change the tension, and that's really what the tuning pegs are for, these tuning pegs here, if you turn it one way or the other, it curls up the string a little more. It doesn't change the length. The length is still from the tuning peg to the bridge, but you're changing how tightly it's stretched. By changing the tension, let's say you increase the tension, the tighter stretched string means the wave is able to travel faster. Higher velocity means higher frequency. So by stretching the string tighter, you get a higher note. By letting it go a little more slack, you get a lower note. So this is how you tune it. You're not changing the length while you're tuning it, you're just changing the properties of the string itself. And in addition to tension, the density of the string also matters. Density in this case, we usually call this linear density. Usually we define density as mass per unit of volume, but for string, we usually talk about the linear density, mass per unit of length, like kilograms per meter. And the linear density matters as well. A thicker, denser string is going to allow the wave to travel more slowly. And you can see this in the strings themselves. The strings are different thicknesses, different densities. And we do that when we're designing instruments so that you don't have to stretch them as tight. So some strings, if they were all the same thickness, all the same type of string, some of them would have to be really loose and others would have to be really tight to get the right velocities. But by having some strings be heavier and some strings be lighter, you don't have to have as much difference in tension. They can all be mostly the same tension. So this is all the physics that, or at least a big part of the physics that goes into stringed instrument design. And this was mostly worked out just by trial and error centuries ago. But over the last few hundred years, we've been gradually learning more and more about why this works. And knowing why it works allows you to be more precise about how exactly you design the instruments. Any other questions on that so far? Increased density, yeah, increased density means the wave is going to travel more slowly because the heavier the string is, the more difficult it is for each piece to influence the next. Like if you imagine a long, thin wire, you shake one end and then the rest of it follows pretty quickly. But if you got a really heavy cable, you shake one end and it takes a lot more time for the wave to propagate because it's so much denser, and more dense means more difficult to move the next piece, the next piece, the next piece. If you want an actual formula for that, the speed of a wave in a string, the tension, more tension means faster speed, so that should go in the numerator. More dense, specifically linear density, means less speed, so it goes in the denominator. However, if you end up checking the units for this, you get, instead of getting meters per second, you get meters squared per second squared when you simplify the units. So you also need a square root there. So more tension means faster speed and therefore higher frequency. More density means a lower speed and thus a lower frequency. But it's not a direct proportionality because of the square root. It's a square root proportionality. So for instance, if you multiply the tension by 100, you're only multiplying the speed by 10, the square root of 100. Any other questions on that so far? Another type of standing wave that we also often see is in wind instruments. This approach so far works for pretty much any stringed instrument because to get a string to vibrate, you want both ends to be fixed in place. For a stringed instrument though, instead of a string, we're going to have a pipe with the air inside the pipe vibrating. So let's say you have a pipe. I'm just going to draw several copies of this same pipe. In this pipe, let's say both ends of the pipe are open. If the end of the pipe is open, would you expect the air to be able to move a lot or only move a little bit? Yeah, If there's no wall in the way, then the air is free to move quite a bit. So that means we would expect lots of vibration of the motion of the air. So we'd expect those to be antinodes. As opposed to if we had a wall on the end cap, then the air wouldn't be able to move as much. So in terms of motion of the air, we would call that a node. So let's say we've got antinodes on the endpoints. But what would you have to have between a pair of antinodes? Yeah, got to have a node in between. So the simplest standing wave you get in this case, if you just got a pipe that's open on both ends, you can get the air inside to vibrate in the form of a standing wave, which would look kind of like this, representing that the air in this region, and of course in this case the air is not moving up and down, the air is vibrating side to side. But this notation just means lots of vibration here, a little bit of vibration here, no vibration at the node, a little bit of vibration, and lots of vibration. Next step up, to make it more complicated, we could put another antinode in the middle, and then of course fill in nodes in between. So we could have a standing wave that looks like this. Or we could put in, let's say, 2 more antinodes in between and fill in nodes in the middle of those. So you could have something like this. And so our standing waves for an open pipe would look something like these. However, if we start counting up half wavelengths again, half a wavelength will take you from an antinode to where? If you start in an antinode and you go forward half a wavelength, where do you end up? Yeah, to the next antinode. Because a full wavelength would look something like this. But if you go only half a wavelength, if you think of that as like from crest to trough, but those are both antinodes. So half a wavelength takes you from a node to a node, or from an antinode to the next antinode. And since we want to start in an antinode and end in an antinode, we're still counting half wavelengths. So if you just mark, I find it useful in this case to just mark all the antinodes. Since the endpoints are antinodes, if we just also mark all the other antinodes in between, it looks like we have 1, 2, 3 half wavelengths. This is half a wavelength, this is half a wavelength, this is half a wavelength. Or in the n equals 2 case, if we just mark all the antinodes, I should say, because we're starting and ending in antinodes, we have 2 half wavelengths. Or for the simplest case, n equals 1, the fundamental vibration, it's just a single half wavelength. So we still get overall the same pattern. You've got to have a whole number of half wavelengths. In general, the half wavelength times some whole number equals the length of the pipe. So you solve for lambda, you get the exact same result, 2L over N. Take velocity divided by that wavelength and you get the same formula for frequency. So on a pipe that's open on both ends, you get the exact same result as you would for a string that's fixed in place on both ends. Likewise, if the pipe were closed on both ends, you still get the same result. So this formula for frequency of the nth harmonic, this actually works for any situation on strings or pipes or vibrating metal bars or whatever, as long as both endpoints are the same type of point. If they're both nodes or they're both antinodes, this formula should work. The only difference you get for the pipe is instead of speed of the wave in the string, what's actually vibrating within this pipe? What's inside a flute or a trumpet or whatever? Air, yeah. So that means this V is going to be speed of sound in air inside the pipe. So for a wave, you're going to use, for a stringed instrument, you'd use speed of the wave in the string, depending on tension and density. For a wind instrument, you'd use speed of sound in air inside the pipe. And that tends to vary with things like temperature and moisture of the air itself, temperature and humidity. So this is why, for instance, wind instruments can get out of tune if you take them to a place with a different atmospheric density, different temperature, whereas stringed instruments get out of tune if the heat or moisture or something causes the wood to expand or contract and messes around with the tension in the strings. So they've got to be tuned in different ways depending on the climate. But the wind instrument, you can't really change the speed ad hoc. You can't really change the properties of the air inside the tube very well. So wind instruments, you typically tune just by changing the length. Usually you've got a mouthpiece that you can slide out or in a little ways, or maybe some tube in the instrument that can be extended or contracted to change the effective length. And then playing different notes just involves, for a trumpet or a flute or whatever, using fingerings to change the effective length of the pipe itself. Any other questions on the standing wave stuff? And it looks like the only situation we didn't really cover is if we've got mixed endpoints, like if you've got a pipe that's open on one end but closed on the other, or if you've got like a metal bar that's fixed on one end but free to vibrate on the other, then you'd have a node on one side and an antinode on the other. That's the only case that's going to use a different formula. So we can look into that formula next time. In the meantime, see if you can work that formula out yourself. Try drawing out similar diagrams, but with a node on one side and an antinode on the other, and see if you can develop a formula like this for frequency for that node versus antinode mixed case. So give that a try. Feel free to email me if you have any other questions, and I will see you next time. You're welcome.